This is the second in a series of videos about entropy. In the first video, we drew a series of dominoes to represent the different microstates, and we said the more possible different pictures of dominoes we can draw, the more microstates, the higher the entropy of the system. So let's look at a way to express that mathematically. So entropy is represented by S. So Ludwig Boltzmann came up with a formula to officially represent this in terms of microstates. So he said entropy equals KB times the natural log of W. And I realize this formula probably makes no sense to you because none of these variables mean anything except entropy. So we have entropy, KB. This is our Boltzmann constant, named after Ludwig himself. And this constant is equal to 1.38 times 10 to the negative 23rd joules per Kelvin. So it's kind of a weird one, but this is a constant that's the same for everything. We have a natural log, and then W is the number of microstates. We can see this represents what we talked about in the previous video. If we increase the number of microstates, there's more different pictures of dominoes. We have a higher entropy in our system. So there are lots of different kinds of systems that have high entropy. So let's look at some different properties that you could use to increase the entropy. So if you have the entropy of a system that has more particles in it is going to be greater than the entropy of a system with fewer particles. That's what we drew in our picture before, right? As we increase the number of particles on the dominoes, there were more microstates, and if there's more microstates, there's higher entropy. So those additional particles exist in additional microstates. So really, it all comes down to the number of microstates. Okay, so increasing the number of particles increases the entropy. Now let's change the particles. Let's say if we have a mixture, some of those particles are red and some of those particles are black, like we drew. That's going to have higher entropy than a system that has the same number of particles of just one substance. If we think about our domino picture, we can see why that would be true. So we had lots of different microstates that represented the same thing. We said we could have the red particle on the left side and the black particle on the right side, or we could have the black particle on the left side and the red particle on the right side. And we distinguished those as two different states because this was a mixture and there was more than one kind of particle. But if this is a pure substance, that means that all of these particles are the same, and it doesn't matter which one is on the left and which one is on the right because they're all the same thing. So these would be equal for a pure substance. So that means there are fewer distinct microstates when all of the particles are the same. Okay, so we can increase the entropy by changing the identity of the particles in the mixture. All right, another thing we can do is we can look at the entropy of a system with a high molar mass. That is going to be greater than the entropy of something with a low molar mass. This is a little bit above our pay grade at this point, but if you've taken physics and you've learned about springs, you'll know that if you put something heavy on the end of a spring, it vibrates more than something that's low weight, that's light on the edge of end of a spring. So we know that there's going to be more vibration between molecules for something heavy. And that's really what bonds between atoms are. Bonds between atoms in a molecule are just springs that vibrate. So if we have more vibrations for something heavier, we are going to have more microstates. And I leave you to physics to learn more about that. So suffice it to say, heavier molecular mass, more vibrations, more microstates. And the same thing can be used to describe the shape. We talked about this back in the intermolecular forces section. We talked about linear molecules versus more spherical molecules, the way that those atoms were connected to each other. And this can be explained using that same logic. If you have something more linear, there's more vibration. It can vibrate and take up a larger possible number of microstates. So more on that in upper level chemistry. Okay, so we said that we can change entropy by changing the shape or the mass. We can change the number of particles or the identity of the particles. So what about energy? Because of course we know energy is related because this is a chapter on thermodynamics. So if we add energy to the system by increasing the temperature, that is going to increase the disorder more than a temperature that's lower. And we can explain that using things that we already know. When we increase the temperature, we know that we increase the kinetic energy. We learned this in the kinetic molecular theory. Kinetic energy is proportional to temperature. And what happens when we increase the kinetic energy? These higher kinetic energy particles, if they're in a solid, they're vibrating more quickly. If they're in a gas, they're physically moving around more quickly. And they take up more possible microstates. So they vibrate or move, depending on the phase, faster. And there are more possible microstates. Okay, so let's dig into that idea a little bit more deeply here. Let's dig into the temperature system. Because you probably know more about this than you think you do. You probably know more about how temperature increases the disorder of a substance, because we've talked about solids, liquids, and gases and the orientation of their particles at least 2, if not 3 times. And now we're going to talk about it again. So here's our favorite picture that we like to draw about the phases of matter. Solids, liquids, and gases. Solids are the most organized pieces. The particles are the closest together, and the particles are vibrating a little bit, but not very much. The liquid, the particles are a little bit more spread out. They can move past each other in the solution, and they're not held into a particular ordered orientation, and they're moving and wiggling a fair amount. And gas particles are flying headlong at full speed and bouncing into the walls of the container, taking up lots of space. So if we are to think about the entropy of each of these states, which of these systems would you say has more disorder? We would say, based on our previous point, it's the one with the higher temperature, and gases tend to exist at the higher temperature. So solids are going to have the lowest entropy. They're very well ordered. They're not moving around very much. There's low vibration, there's low temperature, low kinetic energy. Excuse me. Gas molecules, on the other hand, those are going to have high entropy. They're going to be moving quickly, taking up lots of space, lots of possible microstate orientations for them. And so I guess the liquid is just kind of like in the middle. But realistically, it's a lot closer to solid than it is to gas, contrary to this picture I drew that doesn't quite have them spaced evenly. So we're going to say solid is the lowest, and both solid and liquid are way, super way lower than a gas. Gas is going to be much higher in entropy because of how freely mobile those particles are. And another fun thing we can do that we already know how to do from the chapter on thermochemistry is we can observe that enthalpy is a state function. Remember what that means? It means that it only matters where we started and where we finished, and not how we got there, that the difference is the same. So that means we can use delta S to describe the change in entropy rather than looking at the value of the entropy of each individual space. So we know that no matter what the change was, the final minus the initial entropy will always give the same change in enthalpy. So let's look at the change in enthalpy of the different phase changes that we drew in a previous picture when we learned about intermolecular forces. So we know the transition from solid to liquid, that's called fusion. And we are going from something with low entropy to something with a little bit higher entropy. So the delta S change is going to be a positive number. The disorder is going to increase. And that is going to be the same for all steps in the diagram moving in this direction. So vaporization from liquid to gas, that's going to be a positive number. And sublimation, moving from a solid to a gas, that one is going to be positive. So everything up here on the top moving from low to high is going to have a delta S greater than 0. And this is the favored energetic direction. So we like moving towards higher disorder, more evenly spread out like we did with our dominoes. More evenly spread out in the system is favored. And so our opposite direction phase changes, which I have foolishly not left room for in my picture, are going to be the opposite. So if we go from gas to liquid, that's condensation. If we go from liquid to solid, that's freezing. And if we go from gas to solid and totally draw on top of that beautiful sentence that I wrote, we're going to have deposition. So all of these things that go from higher entropy to lower entropy, they are going to have a delta S less than 0. And this is going to be unfavored. So processes that increase the order, like cleaning your room, require energy input. That is unfavorable direction. It is more difficult to clean your room than to completely mess it up. And now that we've talked about phases, let's add in one more piece of information focusing on gas. So we know that gas is off the charts, way more entropy than solids or liquids. And so we can say that just adding gas into a system increases the entropy of the entire system. And this is something you should be able to identify. So here's an example. If we pick one of those phase changes, let's do this one. Let's look at vaporization. If we go from liquid water to water vapor, we remember from our picture that liquid is going to have lower entropy and the gas is going to have a higher entropy. And so our delta S value was up here on the red side. It was greater than 0. It was positive because we had 1 mole of gas on this side and 0 on this side. So let's do another equation. And this one, it's not going to be as simple as a phase change. It's going to be a chemical reaction. But we can use the same information to make a prediction about what the sign of the entropy is going to be for this system. So this is a reaction between PCl3 and Cl2, and they combine to form PCl5. So this isn't a phase change, so we can't find it on our diagram, but we can look at the amount of gas that we have. So on the reactant side, there are 2 moles of gas. And on the product side, there's only only 1 mole of gas. And we know that gases have way, way more entropy than anything else. So if we're moving from a system with more gas to a system with less gas, that tells us that the system is technically becoming more ordered because there's fewer particles zooming around here. And if it's becoming more ordered, it is unfavored. The delta S is going to be less than 0. Okay, so let's go back to our previous page and let's add in those things we learned to the list. So we'll add that the entropy of a gas is much, much greater than the entropy of a liquid. which is greater than the entropy of a solid. So if we want to increase the entropy, we can add more gas particles. And we said that the more gas you have in the container is higher entropy than if you have less gas in the container. Okay, so that was a lot of details. Let's do a quick recap of what we learned. When we drew the pictures of the dominoes, we learned that the most probable arrangement of all of the particles in a system is the one that is most evenly dispersed. So the pictures where the dominoes had equal number of particles on each side, that's the highest possible entropy system. Then we added a formula, and we showed that if there's more possible microstates, we have more entropy. So the farther apart the particles can move, the more they can move, the more energy they have, or the heavier they are, that all of those things increase the entropy. And then when we looked at the particular phases of matter, we noted that gases being at the highest temperature and the most mobile have the highest entropy of any of the phases of matter, and we care the most, they have the greatest contribution to the entropy. And in the next chapter, we are going to talk more about the laws of thermodynamics and how entropy is related to those things.